if you have a system with two electrons in it, each one of these electrons has a spin angular momentum. Well, how do we describe the spin of the entire system? Well, this is the topic for this lecture, and this is what is commonly named the addition of angular momentum. How do we do that in quantum theory? Well, in classical mechanics, it's quite easy to do that because the angular momentum of, for example, two planets are just described by two vectors. And so the angular momentum of the system, so the two planets, well, you just add vectorially, component by component, those two angular momentum. In quantum theory, well, we do not work with vectors, but we work with operators. So what we are going to do is just to sum two operators and then try to find the eigenstates of that new operator that we get. But first, let's describe what is the eigenstates and what are the operators for the two, in this case, two electrons in separate. So I already discussed the generic properties of angular momentum in previous lecture. So that lecture is the baseline for this lecture. And I'm going to describe now what is the angular momentum of both the electrons as if they never seen each other. Well, if we have the two electrons, the first one, so the first electron is described, well, by specifying two operators. The square operator, so the S1 squared operator, and the S1z component of it. Okay? Just recall, from last lecture that I introduced this operator, whose entries is the three components. Each one of the components of this vector are operators that describe the angular momentum, the intrinsic spin angular momentum of that electron. Well, for this case, I'm going just to pick the magnitude, so the S1 squared, so the S2 squared plus Sy squared plus Sc squared, this is what this means, and the Z components of it. So this is from the last lecture, so I'm going to just pick these two operators, because the commute, you can find a set of common eigenstates. And those eigenstates, we already labeled them in last lecture. So S squared, when it acts on its eigenstate, which I named Jm, is going to give us, well, J plus 1, h bar squared, and now you just copy this again. For the particular case of an electron, J is equal to 1f. So this J is 1f. You do this calculation, and it gives us 3/4 here. 3/4, and this is J, 1f here. Moreover, because we are speaking about electrons all the time, we are going to suppress this 1f and simply write just the m. So in this case, this formula must be understood under the context that J1, so the quantum number here, is equal to 1f. Of course, what is m? Well, m is either plus or minus 1f. Moreover, for this ket here is also an eigenstate of this second operator, because they both commute. But what is the eigenvalue? Well, the z component is given by m h bar. Let me put here a 1, because this quantum number is referring to the first spin of our system. And this is m again. Can you see? So far, so good. Moreover, I want to add some indices here to show that this refers to the first system. So I'm going to write m1 here as well. Okay, so m1 is like that. Well, so far so good. The basis of states which are common, so the basis of states which are eigenvectors of these both operators, is given by, so the basis is given by, well, you just see here these ones. So it's plus 1f and minus 1f. Sometimes instead of 1f or minus 1f, people just use arrows. So arrow up and arrow down, or plus or minus, suffices. This is already discussed in previous lecture, but I'm going to keep the notation of 1f and minus 1f, because it's going to be easier than to do the calculations. Especially if this is the first time you're seeing this. So you have this basis. Any linear combination of these basis cats, so gives us a state that describes the spin angular momentum, the intrinsic spin angular momentum of the first electron. Now, you can do exactly the same thing, but instead of a 1 here, you just replace it by a 2. So this thing all is valid if instead of a 1, you have here a 2. Okay? So this is the basis 2. The same cats. So far, so good. So we have just described the two electrons. They are as if they are in different systems. Each system is described by some linear combination of these bases. And, well, what if now you have a system with both electrons? What should we do? Well, what we do, well, you need a basis. You need a basis for this new system, a new basis. Well, we just take the tensor product of these, the basis of both electrons. So if you have now a system, it's just a picture, and this is electron 1 and electron 2. Well, the spin states of this system are described by states of the form. So let me put 1f, tensor with 1f. This refers to the first spin, this refers to the second. And then 1f, 1, tensor with minus 1f, and then minus 1f, 1, this is a 2 here, tensor with 1f, 2, and finally minus 1f, tensor with minus 1f. So this is the new basis that you construct for B1 and B2. So this is the B total, so, or B12. Look at it. You have these two combinations, so you just specify what is happening to the angular momentum of electron 1 and then for the electron 2. Now, notice that these operators, the S1, S1Z, S1 squared and S1Z, and the same thing for the 2, only act on the spaces spanned by B1 and B2. These operators do not act on this space. But what we do now is that we extend these operators into this tensor product space. So we need to explain how these things act in this space. It's quite easy to do. So this is before, this is now. So we want to construct from this the basis for the new states, and we also want to extend these operators into the new space of action, let's say. So let's describe, for now, a new operator. Let's define the new operator S1 squared tilde, and this S1 squared tilde is S1 squared tensor with the identity at 2. The S1z tilde now is going to be defined as S1z tensor with an identity at 2. Moreover, S2 tilde squared is the identity at 1 tensor with S2 squared. And finally, the SZ2 is the identity at 1, the S2Z, this is Z, Z2. So we constructed these new operators from the old ones. But you see, the action of these operators is well defined in this space. For example, if you act with S1 squared tilde on, for example, let's consider this one. So on this cat, this is a 1, this is a 2. Well, you just replace this by this. So let's do it. So instead of this, you just write S1 squared tensor with the identity at 2. Well, how does this tensor product of operators act on this cat? Well, the first one acts on this, and the second one acts on that. So we get the S1 squared acting on the first cat, so like this. Tensor with the identity acting on the second. Identity acting on the second. Can you see? Well, but we know how S1 squared acts on that. Well, it's written here, right? So S1 squared acting on minus 1f here on this cat, okay, is going to give us 3/4 h bar squared. Remember, I suppressed the j here. The j is always 1f. So what this gives us is, 3/4 h bar squared minus 1f1. And as a result, you get 3/4 h bar squared minus 1f1 tensor with plus 1f2. So as you can see, it works. It works as if, so this thing only acts on the first, and then it picks this eigenvalue here that we got earlier. Okay? So the action of this is very similar what we found here. Okay? One thing you need to be careful is to understand that the identity acts on the second one. Okay? And so on. You can repeat the same type of calculation for the remaining ones. I think it's easy to see what the final result is going to be. And this is essentially the basis for this new state space. Okay, given by this, and these are the eigenvalues assigned to each one. Now, let's just organize. Let's organize this basis into a picture. And before I'm going to do that, let me just say something else. Well, from now on, I'm going to suppress this tilde. I'm going to use the notation S1 squared without a tilde here. And it will be understood from the context that it is the extension into the tensor product space. Meaning, every single time you see this, it's not this S1 squared. No, it's S1 squared, which must be tensored with the identity, depending upon whether you have a 1 or a 2 here. Okay, if you have a 2, the identity appears first, and the operator appears second. The reason is that this might be cumbersome to write the tilde all the time, and I think you can understand that if dealing with tensor products all the time, then you just use the old notation. You just need to remember what this thing is supposed to mean. So what this thing is supposed to mean? Well, here is one example. So when you see, from now on, S1 squared acting, I need space. I'm going to erase this. And when you see the S1 squared from now on acting on this, well, it should be understood that this S1 squared is not this one, because this only it is only defined for this B1. There is which is not a tensor product. This S1 squared, well, by the context, means that you need to first extend this thing into the tensor product, meaning you need to add the identity here for the second one, and then act with it. Okay, but I'm not going to repeat this all the time. I'm just going to write S1 squared and then the cat that I need to act on from now on. So I'm going to just suppress these things, and you should understand what this thing is supposed to mean. Okay, so let's do the picture. The picture for our that represents our basis essentially, and that picture is quite easy to see. So on the horizontal axis, I'm going to put the M1. On the vertical one, I'm going to put M2. So what values M1 and M2 take? Well, it's 1f, plus or minus 1f. So 1f minus 1f, 1f, and here minus 1f. So let's just extend this, makes almost a cube. Here, and here, and here. And now you have these corners of the square. What is the meaning of this picture? Well, the meaning of this picture is that each dot corresponds to one of these bases. So this one, for example, M1 is 1f, M2 is 1f. Well, it's this guy, is this cat. This one, M1 is 1f, M2 is minus 1f, so it's that one, and so on. So this is a picture that organizes what is written here. And I'm going to use extensively pictures of this type, rather than enumerating everything. Okay? So far, so good. This is just a summary of these tensor products. But now, let me do the following. Let us make the following observation. I need to erase this. So we are constructing a basis. We just constructed a basis for our spin with 2 electrons. But first, let's do this observation. Note that the S1 squared, S1z, S2 squared, S2z, so this is a set of operators which must be understood already as extensions. I'm suppressing the tilde here. There are extensions into that B12. Notice that, oh yeah, in fact, you can prove it. They all commute. So this set is a complete set of commuting observables. Well, it means that you can find a set of cats, essentially, a set of states, which are simultaneously eigenvectors of each one of these operators. And because you can find it, well, you can label those eigenstates by the eigenvalues, or better yet, you can label them by the quantum number that in turn determine that eigenvalue. Okay? So by definition, what we know, well, we know what we wrote previously. So S1 squared, when it acts on, let me write it like this first. J1, M1, J2, M2 is equal to J1, and again, this acting on this is J1, J2 plus 1, h bar squared, and now you write this thing again, J1, J2, I mean M1, M2, M1, J2, M2. So this cat is written like this because I'm telling you what are the quantum numbers that determine this eigenvalue of this one, which by the way is that eigenvalue. Notice that this number here is 1. That number is determined by the J1, and this eigenvalue, which is this quantum number, determines the eigenvalue of that one, and so on. So this is a consequence of the fact that they are a CSCO. They just commute, and I decided to label the numbers like that. Similarly, for S1z, you have again J1, M1, J2, M2 is equal to M1, H bar, J1, M1, J2, M2. So far, so good. The same thing. The same thing will happen if instead of a 1 you put here a 2. Can you see? The same formulas. So this is just a consequence of the fact it says a CSCO. You have this definition. And let's make a picture to organize these bases. By the way, before I'm moving into that, remember that I'm specifying that J1 is equal to J2, which is equal to 1f. And as a result, this number, complicated number here, turns out to be just 3/4. Always the same number. the M1 or 2 is always either plus or minus 1f, plus or minus 1f. Well, because J1 and J2 are 1f. That's it. Now let's make a picture for it, for this thing. So, by the way, since J1 is equal to J2 is equal to 1f, and those numbers are the same all the time, I can now simply suppress the j's from our notation. Okay? But I'm going to keep it here, but soon I'm going to suppress them. Again, you can make a picture that organizes these bases, and again, it's a similar picture, the same picture as that. That one. This is 1f, this is minus 1f, here is 1f, this is minus 1f, and so on. The same picture here. Now, this picture comes from the fact that it's a CSCO. This picture comes from the fact that each one of these states are eigenstates of the extended operators that we saw previously. These are also the extended operators, the commute. Now what I want to tell you is that those cats here, so these dot points, the cats here of the basis, are the same as those. So you can make the following assignment. So M1, M2, I'm suppressing the j's by the way, is defined now as being M1 tensor with M1 here, tensor with M2 that you find here. Can you see? And so on. So each one of these points corresponds to this one corresponds to that one, and so on. Okay? This is a definition. They both agree. So you just you see. Let me say this. If you did not know this, forget about it for now. And you already knew that it's a CSCO. This is the only thing that you can write. You just label the states by the quantum numbers. That's it. This is all you have. Well, of course, they are orthogonal. There are the things you can prove, for example. You can about them, but you are stuck with this notation. Well, if now I define from the individual S1 squared and S1z and S2 squared and S2z for the individual operator, I define from those, I construct these tensor products. Well, I see that those cats are also eigenstates of these operators. They have the same structure, so they must coincide. Okay, that's it. So the reason I'm telling this is a rather obvious assignment, is that soon you're going to make something very similar, but the same idea, but the same kind of assignment. But I want that you keep in mind that if you know this is a CSCO, the only thing that you can do is to label the eigenstates by the quantum numbers. Well, what this thing is supposed to mean? Well, it's an eigenstate. This is written, but if you want to give further meaning, well, you need to relate these cats with something else. And in this case, we just related these cats, or this one, with something else, which you find here, which in turn, you know, is just a tensor product of the individual quantum states when the electrons are separate. So we just gave more meaning to what this thing is supposed to mean by this definition, okay? Well, so far so good. You just constructed the eigenstates for our space. Well, what we want to do now is to construct a new basis for our state space. By the way, the state space I did not give it a name. Let me give a name for it. Let me call it the E. J1 is equal to 1f. J2 is equal to 1f. So the basis for this is these four cats. So I want to find for this state space that describes the entire spin, the spin angular momentum of the system with 2 electrons, I want to construct for it a new basis. Well, if I want to construct a new basis, well, I can specify a new set of commuting observables that you find here. So let's do that. let's introduce a new set of commuting observables. And that new set is going to be like this. It's going to be the S1 squared, S2 squared, S total squared, and S total. Instead of total, let me write 1, 2. It's probably more intuitive. 1, 2, 1, 2, Z. You can show, by the way, before, let me just say what this thing is supposed to mean. S12 is equal to S1 plus S2. This is, again, a vector whose entries are operators. The S1x, S1y, S1z, and so on. Again, you can show, before going into the show, these must be understood as extensions into the tensor product. We are working with this again. Now, you can show that this thing is a CSCO. They all commute. Is a CSCO. Okay. So we can find, you can find a set of common, you can find the basis of common eigenstates to all these operators. That's it. And you can, as a result, you can label them, those eigenstates, by the eigenvalues for each one of these. So let's do it. Let's define that basis. So let's start with this one. Again, S12, the S12 that I wrote here, is a new angular momentum. It is a new angular momentum because it's a sum of two individual angular momentums for the electron 1 and electron 2. As a result, you can go back to the previous lecture and see, well, this is just one more particular example of the J that we saw previously in the previous lecture. As a result, well, the same kind of eigenvalue equations hold for S12 squared and S12Z. I'm going to write now those equations that we found for J now for this case here, the S12. So the S12 squared, when it acts on the ket J1, J2, let me put here a comma, like this, and then you find here the S12 and the M12. When it acts, well, it's going to give us S12 plus 1 h bar squared times this state here again. So the same thing, right? This times that. Everything is fine. The S12Z is easier, so it's the J1, J2, S12, M12 is equal to M12 h bar, and then this ket again. Okay? Again, you can see the J1 and J2 are always 1F, so we are going to suppress this thing here from the kets to make it easier. Moreover, we know from the generic angular momentum theory that we found in previous lecture that, well, M12 must always be in between minus S12 and S12, right? That's it. Well, now is a crucial moment. We do not know yet what are the values for S12 and M12. That's it, we do not know it. But there is something else that we know about this. There is something else that allows us to get those numbers. This thing we know, but there is something else that we know. We know, for example, that S12Z, this is important now, a key tool to unlock these numbers. S12Z is the S1Z plus S2Z. It understood as extensions into the tensor product. This operator is just the sum of these two operators. This tells us something very important. I know how this thing acts on the old basis here. I know how this thing acts on the old basis because this thing is written as operators that for which I know how they act on the old basis. How they act? Well, it's written here. That's it. This is very important. So let's act with S12Z on each one of these states. Okay, I'm going to do this in general. So S12Z acting on M1, M2 here must be, well, is S1, let me write it, is S1 squared M1, M2 plus S2Z, I'm sorry, not squared, Z, Z M1, M2 here. I need more space. So let me erase this part here. Now, how does this thing act on that, and how does this thing act on that? Well, you just use the definition here. You see, it's going to give us M1 H bar. So, as a result, from this one, what you get M1 H bar, and from that you get plus M1 H bar. All of that multiplying M1, M2. Of course, let me just suppress this. Put the H bar here. As a consequence, what we know is that M12 is this M12 here. Can you see? This M12. Just compare this formula with this formula that I just wrote. S12 acting on that is giving us this. Can you see? Can you see? When S1, let me say it again. S12 acts on this cat from the old basis here. From it, we know that you get M1 plus M2. But this is also an eigenstate, right? So this M1 plus M2, by the way, it's M2, must be the values that M12 take. This is very important. This is very important. So you to recognize that this is M12. Of course, M1 and M2 might not be, are not, sometimes they are, the other times they won't, as you're going to see. These cats are not those, first of all. But they are also eigenstates of S12Z. This is the key point. These cats are eigenstates of S12Z, but so are these ones. Okay? Because again, we are working on the same space. So you can find other eigenvectors. In particular, this one. So M12 is given by that. Well, but we know what M1 and M2, what the values that it takes. Well, it's here. It's here plus or minus 1F. So as a result, what are the values for M12? Well, the M12 values are as follows. They are, for example, when you get, for example, minus 1F, you get minus 1. When you get minus 1F plus 1F, you get 0, or plus 1F minus 1F is 0, so it can be the value of 0. When they are both 1F, you get 1. So these are the values possible for M12. That's it. So far so good. We get those values. But now, what are the S12? What are the possible values for S12? For those quantum numbers here? Well, we can use this relation and this fact to guess what S12 is. And we are going to argue pictorially. So let us make a picture now that organizes this basis here. Okay? So for that I need to erase something else, because there is no more space. So let's see. I'm going to write now a picture for this basis here. And let's see. Let's see what we find. Now, let me put on the horizontal axis the M12, and here the S12. This essentially is a graph that summarizes these eigenstates. Well, we know it's 0, 1 or minus 1. That's it. That's what you just computed from here. And from the fact that J1 and J2 are equal to 1f, they determine M1 and M2. But now, let us imagine, what if M12 is 0? If M12 is 0, then, you see, let me just put it in another way. If you knew what is S12, it's easy to get what is M12. Okay? It's easy. If you get this, you can get that. It's easy. Now you are asking the other question. If you know what values this thing take, what are the intervals? So let's get it. If M12 is 0, well, one possible value for S12 is exactly 0. Here. If M12 is equal to 1, for example, if it's equal to 1, let me just write it. You can have it here, S12 and 1 as well, here. Can you see? So all these three dots, can you see, with S12 is equal to 1, guarantee this thing here, whether it's 1, in fact, whether it's 0 again, or minus 1. Can you see? I'm trying to guess from each one of these values what S12 must be. Notice that if you can now check it, if S12 is equal to 1, well, then M12 is between minus 1 and 1. Well, that's true. It's here. Minus 1, 0, and 1. If S12 is 0, then it's between minus 0 and 0, which means that M12 is exactly 0. This case. Okay? This is why this step is so important. If you know this definition, you know how it acts on the old basis. From that, you get the M12 values. But now, from this problem, you can guess what the S12 are based on a picture like this. Can you see? Very important picture. Each one of course, each one of these points corresponds to one state here. You see? Just specify M12 and S12. Now, what do we have more here? We have the following idea. We just identified the several possible states. But now let's analyze something else here. You recall the ladder operators, right? You recall the ladder operators. Here we find, by the way, here we find something that we in the previous lecture called the E, this J something. Now here is the E, 1, 2 is equal to 1. And here is the E, S12 is equal to 0. Subspaces of the subspaces of the E, J1 is equal to 1f and J2 is equal to 1f. Again, these points are also a basis, represent a basis for that space. More, the ladder operators. The ladder operators allow us, let's call it the S12 minus, to map between these two states, S12 minus. And we can also have, the plus, S12 plus and S12 plus, the ladder operators, if you remember from previous lecture. Let me write here the ladder operators, because we are going to use them soon. So the S12 plus is equal to S1 plus S2 plus. Okay, again, extended, understood in the extended sense. So this only acts on cats of the first electron. This only acts on the electron of the second. Only acts on the electron on the second electron. So this must be understood tensor with identity at 2, this must be understood with tensor product with identity at 1. In turn, S1 plus and S2 plus are understood as S here. Maybe put S plus 1. But I'm going to write it later. It's probably better. Let's just focus on the picture first here. Okay. So this is the definition, okay? You just act like this. Moreover, we also know something else in these pictures. I said that M1, M2 are eigenstates of S1, 2 with eigenvalue F1 plus M2. So, for example, this state here as eigenvalue is equal to what? Can you see? It's 1f plus 1f. So it's equal to 1. So let me say this cat here represents is a basis vector for the E M12 is equal to 1. On the other hand, these two states here, notice what is the M12 for both? Well, it's 1f plus minus 1f, which is 0, and it's 1f plus minus 1f, which is again 0. So this is the E M12 is equal to 0. And finally, this state here is the E M12 is equal to minus 1. All a consequence of this formula here. But now here's something interesting. We also find here, can you see? M12 is 1. So this is E, M12 is equal to 1. Here, we find the E, M12 is equal to 0. Can you see on the horizontal axis? Here we find the E, M12 is equal to minus 1. Notice the dimensionality. This is one dimensional, this is one dimensional, this is two dimensional, this is two dimensional, this is one dimensional and one dimensional. This is a basis for this space. This is one direction, so it's like a line. This is a two-dimensional space, like a plane, like this. These two bases span this space, the EM120, and so do these basis states, and so on. This also is a basis, just like this. This is very important. It's very important because, again, because this is a complete set of commuting observables, the only thing that we know is to write the states labeled by the quantum numbers that determine the eigenvalues of all these states. This is how much we know. They are orthogonal if the quantum numbers are different. We know that M12, we know these constraints, but that's all we know about these cats. What these pictures now allow us to do is to relate these bases with the old one. Very important. You see, you have two CSCOs. The one which has, let me write it, the old. Let me write the old one. You need to remember the old CSCO. CSCO was S1 squared S1z, S2 squared S2z. This is the old one, right? It determined these bases. You have a new one that determines these bases for the same state space. The E, J1f is equal to 1f, and J2 is equal to 1f. Can you see? So somehow these two bases must be related. And by doing that, by relating these bases with that one, so by relating these two, it gives new meaning to this cat. Because right now it's just a cat labeled by numbers. So you can express this basis in terms of that basis, and this is our task now. See? So let's do it. I need to erase quite a few things now, because this is... Let me erase this. Erase this as well. I think this is enough. So let's look at the picture. Let's start from, well, okay, there are several ways to start, but let me start from in this way. Look at this E M121. Is M12 is equal to 1. It's the same as that. This cat here is, well, I know, this cat here, I'm sorry, this cat here, it was the, let's write now the quantum numbers. This is the quantum number for this one is 1f. The quantum number for this one is 1f. I'm going to suppress those. The quantum number from this, well, it's 1. Let me write it. S12 is equal to 1. And the quantum number from the last one is 1 as well. Please, just note, this is a quantum number. This is an operator. I could put here a at to distinguish them. By the way, let me just, okay, of course. I wrote here an m. This notation also works, but let me put here a m, 1, 2. I think that's what I wrote here. Sometimes I use one notation, other times the other notation. Let's skip the m to remind us that, well, this is an operator, this is a quantum number. The m. S12 and this. This is the representation of this cat. Well, it must be the same, right? If this is an element of the base, this is another element of the base, well, let's make them the same. So you get here, the M1 is equal to 1F, tensor with the M1 is equal to 1F. You see? So this is the first connection we establish between these, the basis for this CSCO and that basis for this CSCO. But now something wonderful is going to happen, because if I know this connection, I can know all the others. Why is that? Because now I can act with S12 minus on this state. It gives me this state. Let's do it. So S12 minus, acting on the state S12 is equal to 1, M12 is equal to 1, is going to give us, please, I hope you remember the formula. Now I need the formula. I just need the space to write it. Let me put it here. So the S12 minus, acting on S12, M12, is going to give us, by definition, we already addressed this issue last lecture. So it's h bar, and then a complicated square root, and then S12, M12 minus 1. I hope you can see it here. So it's the cat now becomes M12 minus 1 here. Okay? This complicated number is S12, S12 plus 1 minus M12, M12 minus 1. Can you see? Now I'm going to use this formula here. So it's h bar here, a complicated square root, and then the same cat that we find here, but with the M12 here, minus 1. So S12 is equal to 1, remains the same, because again, we are acting on this layer, so the S12 is the same, so you just move from here to here. And now, but the M12 on the horizontal axis changes, so it becomes from 1 to 0. Okay, now let's compute this complicated number. So it is 1 times 1 plus 1 minus 1 minus 1. Of course, this is going to be 0, and this is going to be 2, so this is the square root of 2. Okay? So we just acted with this on this side. Now let's act with this thing on the other side. minus on this tensor product. So let's do it. I want to make the notation shorter, otherwise I don't have space. Let me just combine these two into M1, 1F and then 1F. It's easier than me 1F and then 1F. Okay? This is just notation for that. Remember, it's a tensor product. This thing now is S1 minus plus S2 minus, acting on this cat, 1F and 1F. Of course, in turn, you just do the distributive, right? This one acts on this one plus this one acting on that one, right? So let's write it. Let's write it immediately, the answer. So be h bar, a complicated number, and you get 1f minus 1f, plus this one acting on this one. So this plus, by the way, is this plus here. H bar, a complicated square root, and now we'll lower the second. So it's 1f minus 1, like this. Is it fine? Now let's just get those numbers. What those numbers are? Well, the j is always equal to 1f, the j1. So it's j1 times j1 plus 1, so it's 1f plus 1, minus the 1f minus 1, right? Good. The same number here is here the number is the same. Okay? Now what number is this? Well, let's just compute it. So it is say 1f plus 1. So it's 1f plus 2 divided by 2. So it's 2 I'm sorry. Plus, let me just write it like this. So it's 3f's times 1f is again 3/4, right? But this thing here, minus, it's 1f minus 1, which is minus 1f. Minus 1f times minus 1f is plus 1/4. So this thing is 1 here. So it's dramatic simplification. And what you get is essentially h bar, this one, minus 1f, plus 1f minus 1f. Can you see? This cat is that cat here. Let me just show it. This thing is this thing. Can you see? I just acted with S12 minus on this side and on that side. They are related. So, let me just write it now. The S12 is equal to 1, M12 is equal to 0. Just rearrange it. You just divide by h bar square root of 2 on both sides. This here cancel. The h bar cancel here. So we get 1 over square root of 2. 1 over square root of 2. And now, well, you get the minus 1f plus 1f minus 1f. What you see, what you have here is what you have here. Okay? Can you see? So that's it. This second state here is a special linear combination of these two states. Namely, you want 1 over square root of 2 of this one and 1 over square root of 2 of that one. That's it. So let's summarize these ideas. Let me put it here, because space is needed. I need to erase that. So you get S12 is equal to 1, M12 is equal to 0, is equal to 1 over square root of 2, minus 1f plus 1f minus 1f. Okay, now I need to erase everything here. Because now there is a very important key step that we need to make, and we need space for it. We want, you see, We already know what this cat is that one. We already know that this cat is a special linear combination of these two. Now let's get that one. Well, there is no ladder operator. If I act with a ladder operator, I get that one. Fine. But I want that one as well. Well, the way I get that eigenvalue is that I first specify what I know about that eigenstate. Here's what I know. What we know. What we know about it. So what we know, well, we know some constraints about it. First of all, this state lives in E m12 is equal to 0. So this cat must be some linear combination of these two states. So the S12 is equal to 0, m12 is equal to 0, must be some linear combination of both. So some C1 from that one, so minus 1f, plus C2, 1f, minus 1f. Fine. This is what we know. More. It is normalized. So C1 squared plus C2 squared cannot be anything that we like. Well, it must be something that is equal to 1 when squared like that. Moreover, we also know that this state here must be orthogonal to that one. Very important. And so when you compute here S12 is equal to 1, M12 is equal to 0, dot product with S12 is equal to 0, M12 is equal to 0, well, you just multiply the coefficients. The coefficients here are 1 over square root of 2. So it's 1 over square root of 2 times C1 plus 1 over square root of 2 times C2. And that thing must be equal to 0. I think this is enough because our unknowns are C1 and C2. We want that special combination. So let's see. From this equation, we know that C1 must be minus C2, right? Let's substitute here. C1 squared plus, well, we put here the C2, and you get C1 squared again. So this is 2C1 squared is equal to 1. Well, one possible solution, remember, this is the complex, this is the absolute value of the C1, so it might be a complex number, but I just want a solution. So I'm going to choose this as being just a real number. Okay? I'm going to not include the imaginary part, because I just want a solution for it. That's it. Well, let me write it. So you get C1 is equal to 1 over square root of 2. With all this information now, I can just substitute here. 1 over square root of 2 times this minus that. Can you see? Because it's C1 is 1 over square root of 2, it's here, and C2 is minus C1, by the way. Okay, maybe I put it here, like this. It's minus square root of 2, minus square root of 2 times that. Is it fine? So here it is, again, a state, a connection, let's say, between this cat here of this basis and the old basis, which is that linear combination that you find here. Okay? Now, what about the last one? The last one is easy. We could again act with a ladder operator, S12 again, minus, on this one. So act on these both sides with S12 minus. I'm not going to do that because it's obvious. This cat must be that cat. So that cat. So let me write it. The final one, which is S12 is equal to 1, M12 is equal to minus 1, must be that one. So let's see. It's M1 minus 1F plus, minus 1F. Again, like that. So it's the same, this one. I'm suppressing again the tensor product symbol here. Okay? So these two are the same. So let's see. Let's just summarize everything that we found. We know this one. We know this one. And let me just summarize here the states. We also found this one. So it says S12 is equal to 1. M12 is equal to 1 here. Which was that one. So the 1F, 1F. And finally, we have this one. So I bet you just summarize everything in one spot. M12 is equal to 0 is equal to 1 over square root of 2. The minus 1F, 1F, plus 1F minus 1F. Okay? That's it. The entire relationship between the new basis and the old one is given by that. Now, this space here, one step at a time. The ES12 is equal to 1 is spanned by this. ES12 is equal to 1. There are three cats here. It's a three-dimensional space here. This is what we call each one of the elements, then is called an element of the triplet. So this is a triplet. Because there are three states in it that span this subspace here, this layer. Of course, the space downstairs here, the ES12 is equal to 0, well, it's one-dimensional, so it is a singlet. So the S12 is equal to 0. These are the names of typical names that people use to call this thing. Notice again, I'm suppressing a lot of notation here. I'm suppressing many times the J's here, because otherwise I would have space to write anything. And it becomes cumbersome. The context tells you what this thing is supposed to mean. So this is how you add, see, this is how you add two angular momentum in quantum theory. You add the operators, you see. First you have them separate, the operators separate. You describe the electron 1 and the electron 2. This is the old basis. Two things separate. Well, you get the basis for it, it's written here. Because this is a CSCO. Now you add the angular momentum, meaning in quantum theory, means you add the operators, you get the new CSCO. Well, you see, since it is a CSCO, well, it has a set of common eigenstates written here. But these cats span the same space as that, so there must be a relation between both. And the biggest test that we have to do is to relate those two bases. Okay, so you add the operators, and you need to know what are the eigenstates, but to give further meaning to those eigenstates of these, we relate those eigenstates with the old ones. This is what we have done here. Now, that's pretty much it I have to say to add to angular momentum. Now, next lecture let's add a third electron on top of this one, and so we have a system with 3 electrons. But the ideas that I'm going to use next lecture are pretty much already said here. We again to define a new CSCO and to relate that new CSCO with the old one. That's it. That's what we are going to do. This lecture, adding to angular momentum, already contains the main ideas to add now a third one. That's it. So I hope you like it, and see you next time.